And thank you for joining us. We've got some really cool space stuff we want to talk about. Athena, why are you excited?
Because there's nanodiamonds in space.
That's awesome. Yeah. And Mike, why are you excited?
Oh man, because Russia pulled off an epic space flight this week.
And then Ben has an interview for us on the observation deck. Ben, why are you excited?
Well, I'm excited because we've got Emory back, who has had some of our most popular shows under the TMRO brand for quite some time, joined by Craig, and we're going to be talking about the SmallSat conference. It's going to be a lot of fun.
And then we have questions and comments from you, the community, in our third segment. So stick around. Tomorrow, Orbit 11.32 begins right now.
Good morning. How's everything up in the sky?
All right, now at the top of the show, we always like to start with some launches. So, Space Mike, take it away with our lightning round launch minute.
Well, over this past week, we had a Delta IV Heavy launch. This launch happened from the Space Launch Complex 37 in Cape Canaveral, Florida, and it occurred on Sunday, August 12th at 7:31 Coordinated Universal Time, and it was launching NASA's Parker Solar Probe, which is going where no probe has gone before, into the sun's corona at a distance of within 6 million kilometers, or 3.7 million miles for those in the United States. During its mission, Parker Solar will seek to answer some really important questions, like why and how is the solar wind accelerated to supersonic speeds inside the corona? What is the mechanism that heats and accelerates those particles in the corona? And why is some of the particles, very few, being accelerated to near the speed of light, creating highly energetic particles? So these are a lot of the important questions that this probe is going to be answering for us. And congratulations to United Launch Alliance and to NASA for the successful launch of this mission. This was beautiful. Oh, man.
And 0. That's awesome. What a really cool launch. Now, it was the Parker Solar Probe that launched, right? Is Parker
right.
Solar Probe, is that named after somebody?
It is, in fact. It's named after Eugene Parker, who did a lot of work in the early 60s about figuring out why and how a lot of the mechanisms for the solar wind happen. And he was there at the launch,
oh my goodness, this is him.
A spacecraft named after him. He's the only living person that has a spacecraft named after him. So I just think that that's really awesome that he was able to witness this and hopefully see a lot of the data back from this so that his research can go even further. So that was just amazing.
He looks so excited. That's so cool.
Oh yeah, go ahead, sorry.
Oh, he just looks so incredibly excited to be able to watch this.
Absolutely, absolutely. And something else that I think that is really exciting about this, I mean, the main reason that we want to study this and have it go into the sun's corona is so that, I mean, all the different solar flares not only can hurt astronauts that are in the space station or future going into deep space, but it can also fry a lot of our electronics and mess up the modern infrastructure that we rely on today. And especially for those particles that can accelerate to near the speed of light, it makes me wonder if we can understand what is causing that. Could that potentially enable our future to have some sort of equivalent of a warp drive or a hyperdrive or something like that? I don't know, but hopefully we'll get a lot of really great data back from this probe once it finally reaches its orbit around the sun.
Yeah, I hope so too. And this probe is going really fast, right? Like, isn't it the world record holder of like most fastest object like that we've launched recently? Like, why does it have to go so fast?
I'm not sure about that. I do know that it's the fastest one that's done like an escape velocity out of the sphere of influence of the Earth. But I'm not sure if it's the fastest or not. I'm sure the people in the chat room might know for sure, though.
And we also had a question from Jim Burr off of YouTube in our chat room. They wanted to know, how does the probe get so close to the sun, and what's the heat shield made out of? Do you guys know?
Well, it's not actually, a lot of news reports have said that it's going to be touching the sun, and it's not directly going to be touching it. It is going to be flying within the corona, and the heat shield is made out of, I mean, I'm not sure what generation it is, but this has to do with a lot of the different Pika stuff that, you know, SpaceX picked up. That technology and turned it into Pika X. But the heat shield for this is very powerful to be able to protect the instruments. And that heat shield is always going to be facing towards the sun so that the instruments on board this probe don't get fried. So
nice.
If you want more details about that, we'll have to talk about that another time.
Yeah, cool. And so how many launches does that make for the US in total this year then?
Oh man, so this is the 22nd launch for the United States so far this year, the 22nd orbital launch. So as of right now, the United States is tied with China. So pending any other surprise launches this week, we're neck and neck as we've been pretty much all year. So very exciting. I can't wait to see who launches the most by the end of the year.
Awesome. Thank you so much, Mike. Now, Athena, for your story, I was getting super excited because it's about things that sparkle, and I love everything that sparkles. So can you tell me a little bit about these nanodiamonds that we found in space?
Yes, so nanodiamonds actually form from something known as nanoparticles.
Wait, what's a nanoparticle? Is that just a really small particle?
Very, very, very tiny particle, yeah. So it's on the nanoscale. It can only usually be detected by a microscope, but they're actually found around the disks of that orbit newborn stars, and such as this image, protoplanetary disks. So this is actually in the Orion Nebula, and I love proplyds, protoplanetary disks, because this is where newborn stars start to form. Because of their really strong amounts of gravity, they start spinning really fast. They start to attract all nearby dust and gas, and disks will start to form. And these nanoparticles contain all the necessary elements for planets to form. So
what are those elements?
So it contains carbon, it contains nitrogen, there's actually, of course, hydrogen, helium, which is very abundant in these regions. And actually what's exciting about nanodiamonds is there's some regions with them where they actually, the reason they're called nanodiamonds specifically is because they're composed of carbon. So they have a hydrogenated substances, so hydrogenated molecules that cause them to reflect light a certain way that makes them kind of like glittery. So like this next image, you can see that literally it's sparkly, it looks really cool, and it's because there's some regions of our Milky Way that literally goes overhead here on Earth that contain these nanodiamonds, and they literally reflect light in certain ways, and this is how we're actually able to detect them.
What kind of instruments were they using?
Yeah, so they were using spectrographs that are found on a lot of instruments out there. It's like orbiting satellites and also like telescopes to detect different elements that are present in certain regions. And so with nanoparticles, they were able to, nanodiamonds, that's how they were able to actually figure out where a lot of these were actually found. And what is really super exciting for me is this is tied directly in with the AME, which is the anomalous microwave emission.
Which is,
and you guys might have heard of the cosmic microwave background radiation, so it's a similar type of acronym going on. But the anomalous microwave emission is there's certain regions in space where there's higher levels of infrared radiation that have been detected than what would have been estimated or calculated based on those certain regions. So if you get a certain region of the sky and because of what's actually present there would only be about a certain amount of radiation you would actually detect because of the amount of planets that are present or the amount of stars that are present. But there was much higher levels of infrared radiation that was detected. So this was an anomaly. So they called it anomalous microwave emissions. And they found that there is direct evidence that because of these nanodiamonds that are spinning around newborn stars, they're giving off that excess infrared radiation, which can explain the AME.
So the stuff that we're detecting from the nanodiamonds around a newborn star with a protoplanetary disk that forms a planet is the same signature than the problem that we already had with the AME. We didn't know what the anomalous microwave emissions were.
Yes.
So they line up together.
Yeah, there's actually a direct comparison because there's actual equal measurements that were being made, and it's made of the exact, like you said, the signature, the same actual signature. It matches up of the same elements that are present, the same type of radiation that was measured, and the same reflections. So they're like, wait a second, this is exactly what it is. This is exactly what we've been trying to figure out. And it's been a few decades. So the AME actually has been worked on for a few decades now. So I mean, the fact that we got to figure it out now as opposed to hundreds of years from now is pretty nice. But yeah, so that's what they ended up matching up, is those directly next to each other, which is very exciting for me. And I just like it too because they're crystals that are in space and
they're sparkly.
And they're sparkly and they're in proplyds, which again, I mean, for me, I'm always passionate about trying to find life beyond Earth. And so if we can find this and we can find that something like this is happening around newborn systems that might later translate into exoplanetary systems, that's great because it's also found here in, obviously the Milky Way, and we see it overhead at night. So.
Do we find nanodiamonds anywhere, like other nanodiamonds on Earth that we?
Yes, actually. So meteorites. So sometimes pieces of rock can break off of celestial bodies out in space. And so if there's regions, maybe like from a disk that started to form and these nanodiamonds were present in it, they actually can break off, fall into our orbit. They can get pulled in by our gravity. If they can survive our atmosphere, they'll crash land here on Earth. And nanodiamonds have actually been detected in meteorites that have landed here on Earth. So we have some of our own nanodiamonds as well.
With detecting them here on Earth as well, does the nanodiamond, like when you detect them, does it look different to normal diamonds? Because like both are made of carbon, right?
Yeah, so I haven't actually visually seen images. Oh, that's awesome.
Yeah.
Okay, cool, very cool. So Astro YYZ. I personally haven't seen any direct images, but based on my understanding of how actual diamonds, they are carbon-based, and nanodiamonds are carbon-based, they will have a visually similar structure to them, just because, again, I was reading that they do have this hydrogen molecule-based substance to them on the exterior, the coating, which is what causes them to reflect. So they will have a very reflective surface, but because they're on, you'll need to see them under a microscope. They are going to probably look a bit different than actual diamonds, but more like just a very miniature version. I haven't seen any images, so if you guys end up finding like some images of nanodiamonds, that would be awesome.
Yeah, if you have some great ones, put them in the comments below, and if they're really pretty, we might even put them up next show in the comment section.
Yeah, so that'd be really cool. But I can bet they would be the same.
Yeah, it makes sense that the heat from that area is causing this, but I thought that the pressure needed. But then again, it is nanodiamonds, so I guess it's not the same process.
Well, yeah, actually, that's how they go from nanoparticles to nanodiamonds, is because in regions with a newborn star, I mean, they're the billions of degrees in temperature, and because of that heat, and then you have the pressure, and you have the energy that's in that disk, it actually will start to cause its elements to evolve into carbon-based, and they'll actually change from being just nanoparticles made up of certain elements, so hydrogen, mainly hydrogen-based, and then they'll actually turn into these really hot carbon-based nanodiamonds. So yeah, and just like how diamonds are made. Awesome. Lots of heat and pressure.
That's awesome.
Yeah.
So I guess the one thing I took away from that is that there are sparkles everywhere in the universe surrounding newborn stars, or stars that are about to form solar systems. So that's amazing. But Space Mike, tell us a little bit about the Russian spacewalk that just happened.
Yeah. Oh man, I am so excited for this because it was beautiful footage, but they were also doing a lot of science with this as well. And they almost broke the record that was set just a couple of months ago for the longest spacewalk that Russians have done. But with this mission, oh man. This was a mission that Oleg Artemyev and Sergei Prokopyov spent, and this was just over this past week. And they actually installed a couple of instruments on the outside. They installed an instrument called Icarus to the outside of the space station, and they also deployed several CubeSats by hand. And here you can see several of those CubeSats that they launched, and you can see the demonstration there where they just can grab onto the handle and then throw them. Although this time they weren't quite having a competition between each other of who could throw it the farthest. So it's not quite the space sports that I was hoping that it was going to be. But that's okay.
Like
that's
crazy.
okay.
Like that can't be that accurate. Surely that's not that accurate, Mike. Like, don't you need to precisely like you're ejecting a CubeSat from like I don't know like a deployer and it just shoots out, pops out, goes in the exact direction it needs to go. But this guy just like threw it and it's like spinning around. Like. Is that okay?
Yeah,
Can
absolutely.
those CubeSats, like,
no, it's not very accurate. And even this, when he just tossed the second one you saw there, they were asking him on the comms, like, hey, can you throw this just a little bit higher this time? But the thing is it doesn't necessarily need to be accurate because when they're throwing it in the opposite direction that the space station is going, they're ensuring that it's not going to come loop around and hit the space station on another orbit. and it's going to deorbit within 1 to 3 months anyway. So it's not really that big of a deal, especially with these ones for how accurate the orbit is or anything like that. And just for information, the satellites were 2 of them. The Tanyusha were experimenting with 3D printed parts, so they were just technology demonstrators to see if 3D printed parts would survive in space. The other ones are called SiriusSat, as in like the star system Sirius. And those were actually doing space weather, looking outwards instead of looking in. And all of those were actually built by Russian university students. So that's really cool.
Nice.
Wow,
And
university students.
do the Russians actually go out, is this a common thing for the cosmonauts to just go out and like throw their CubeSats, or did they go out and do this mission or this spacewalk specifically for that?
They didn't do the spacewalk specifically for that. Again, they were installing an instrument called Icarus, which is basically a glorified bird watcher. It's tracking the migration patterns of small animals across the planet to just find out different patterns about that. And there's also potential to see if that has any correlation to the spread of diseases. And they were also collecting some samples that were in a materials science bay on the Zvezda module. So, in fact, they were going to actually grab 4 samples, and they only had the time to grab 2. So, because their spacewalk had already gone for quite a bit longer than they had planned on.
Throw it higher.
I think it was planned for 6 hours, and it went like 9 hours long. Yeah. What was that, Lisa? Sorry.
Oh, I said like they spent too long trying to throw the CubeSat directly like where it needed to go.
Sports.
Spent too much time playing CubeSat ball. Cool.
That would be funny. Oh man, I think what they actually took so much time though was the actual installation of that Icarus instrument, and that was on the outside of the Rosvet module, or excuse me, the Zvezda module.
Yeah, awesome. Thanks so much, Mike. And if you guys are interested in other people that deploy CubeSats, not by hand, but actually by dispensing, we're going to have NanoRacks on the show on September 8th. So put that in your calendar. We're going to have NanoRacks on. It's going to I amazing. So I'm excited about that.
Yeah, that's super exciting. Yes.
But Athena, you have something else you're excited about too, right?
I do, and it has to do with disks again, actually. But this time it's disks around white dwarfs. So white dwarfs are they're a star that's gone very, very cool. It's usually the core of a star that's died. So actually our sun, in about 5 billion years, eventually is going to cool down to a white dwarf. They get really dense and they cool down. And when they cool, they actually start to attract a lot of that dust and gas nearby
so they make
elements.
So it's not a protoplanetary disk, it's like an afterplanetary disk.
I guess
the planets
post. Yeah, I guess that's what it could be called. I like to kind of compare it to the rings of Saturn. So actually in this illustration here, you can see on the right side that super bright star. That would be a white dwarf, and this is a artist's illustration of what the disks around it would look like. And what's really cool is that scientists, there was, oh my gosh, dozens and dozens of telescopes of universities that contributed to this research. They were finding that there's Earth-like materials. They're actually quite common elsewhere.
How do you define Earth-type material?
So, like a lot of the elements in the periodic table of elements that are found here, where most of our universe is actually composed of dark energy, so 68%, and then about 27%, I believe, is dark matter, and then the rest of it, most of it, is actually about 5% of it is about like basic elements, hydrogen and helium, and then the rest of it is really just like Earth material. So, like what we're actually made of. It's very rare to find. Yeah, so we do find them elsewhere on other planets. There is other elements out there, but it's quite rare. And so the fact that now there's exoplanetary systems that may exist that actually have these other Earth-like materials is exciting. I mean, even potentially water. One of the 18 planetary systems that was studying, they actually found evidence that might lead to them actually finding water also. So that's really cool. Yeah.
So, wait, if we can show that water is now more common, as well as these other Earth materials, what kind of impact does that mean for finding like life out in the solar system? Yeah,
well then it means that there's a higher chance that we'll be able to find life. There's a higher chance that there are other planets, especially too if there's exoplanets orbiting white dwarf stars. I mean, to me that seems quite rare because a lot of the exoplanetary systems that we've been talking about, like through tests, they've been orbiting like low mass stars, so brown dwarf stars. They are very cool stars and they're pretty small. But white dwarfs are you know, they're the remnants of another star. They're kind of like a dead star. You know, they have a very cool core, and they actually can no longer burn hydrogen and helium. So it's really interesting. So they're similar to brown dwarfs. But yeah, so with this, it's cool too because these regions around the white dwarf star are also similar to actually like the rings of Saturn. So similar to kind of like what I was talking about a little bit earlier. So here's an image that I thought was really beautiful. I'll share with you guys from NASA. Is the rings of Saturn, which is made up of a lot of also like excess materials. It's made up of a lot of rocky materials. So, but around white dwarf stars, if there's actually chances that these can collide with one another, planets can form, and then the fact too that we're able to find this. There's actually, I do want to share a quote with you guys from one of the researchers from the paper. Actually, a few researchers kind of put this together. It says that we've actually previously identified one star system. It's 170 light years away in the constellation Boötes. And it was really rich in carbon, nitrogen, and water, giving a composition similar to that of Halley's Comet. So, and it pretty much is cool because it says that it's really similar to like if there was a bulk Earth. So the fact that we found this, and this is only 170 light years away, that's great, you know, and it means that there really are chances out there of there being other Earth-like planets elsewhere, just in our galaxy alone. You know, I mean, I know elsewhere in our universe is cool, but just in our galaxy, is really exciting to try and find other planetary systems. So I think TESS now is going to be also really focusing a lot too on these white dwarfs and trying to find other Earth-like planets.
But aren't white dwarfs, like, don't they have a really strong gravity because they're so condensed?
Yeah, they're super dense.
There's a question in the chat room here from Helio Pausing that wants to know, white dwarfs have a really strong gravity, so is the disk rotating fast? Like, how did we get that information about what the disk is doing?
Yeah, so the disks are rotating extremely fast. I don't know the exact velocity, but they are rotating a lot faster than they would around a protoplanetary disk. And because the thing is, as it's cooling and it is condensing, that's what's actually attracting in a lot of the nearby dust and gas and accumulating it into it. But because it's still getting cooler and cooler and it's cooling down consecutively in temperature, that's allowing for it not to actually be blowing apart all the material because its gravity from its density being so dense because it went from something like our sun down to this tiny little thing, because it has such a strong gravity, that's what allows for all this material to not be completely blown apart.
Does that mean that, so like, okay, you have planets and then you have a star and then it becomes a white dwarf, but then more like of that material comes in and forms another kind of cloud of material. Can planets then form again around the white dwarf?
Yeah, so that's one thing that we're actually looking at and trying to find is that if there's a lot of these elements that are found there, that are found here on Earth, a lot of planets can start to form. They can condense.
Oh, that's
so
cool.
Similar to protoplanetary disks. It's kind of crazy because it's a whole recycling process that's happening in our universe. You have, these newborn stars that are forming and they're starting to form a disk of their own, but then you have these stars that just died. It's like our sun is going to die, Earth is going to be gone, but then by the time it cools down into a white dwarf, it's going to be a whole recycle process again. And there's going to be a whole new potential planetary system that'll form again. So it's like, it gives me chills because that's literally the circle of life, and it's not just here on Earth, it's in our entire cosmological, universe. So it's just got super philosophical, but there's so much science behind it. Yeah, and that's what's exciting, because all of this can seem like, almost fantasy-like, but all of it is real and it's actually happening. So
it's not just, recycling is not just good for us here on Earth, it's also good for the galaxy.
Exactly. I mean, and all of our material is going to be recycled. We're eventually going to be, pulled into our sun as it expands into like a red giant. It's going to puff out its outer layers into a planetary nebulae, and then what's left of its core is going to cool down and condense into the white dwarf.
Recycled material. We are already recycled material.
We are already recycled material, indeed. And then, oh my gosh, not even to mention too, like galaxy collisions, but that'll be another story. Andromeda and us.
It's the circle of life.
Yeah.
So you're probably wondering why Benjamin isn't here in the news deck with us. I think it's probably because there's too much sparkle in Athena's hair.
It keeps flying off. I'm sorry.
Ben, what are you doing out in the observation lounge?
Your news stories while we've been out here, and actually, Dud, I'm going to throw a wrench in your plans. If you could unmute the observation lounge, because we do have some comments on the launch minute. We were talking about the heat shield. We did look it up, and it is not pica because it is not ablative. What was the heat shield on the Parker?
It's just carbon phase sheets on a 4.5-inch thick carbon foam, and it creates a shadow over the the body of the instrument, which is sitting at about 85 degrees Fahrenheit, which is kind of like outside here in Anaheim today.
Awesome. I'm also good. Like, if you could go to your mic pack, I think it might be off.
Might
There you
actually
go.
be
Yeah, just
I'm
just
a
awkward
lucky
moments on the show. There we go. And then the second thing we were talking about right on top. There you
I
go.
thought so.
There you go. Cool. The second thing we were talking about was the speed of the probe, and I was like, that can't be right. It can't be the fastest thing because Voyager, and Vax, you were all like,
no, it's a lot faster. The speed is, and I went looked that up too. I had the right number in my head, but I had the wrong units. I said 430,000 miles an hour. It's 430,000 miles per hour, or 700,000 kilometers per hour, and that translates to 0.0006, the speed of light. Okay, so it's a very small number in terms of the speed of light.
still very fast.
But it's crazy fast, and it's several times as fast as Voyager or New Horizons or any of those. It's going to do 7 flybys of Venus in order to both pick up speed and to do phasing. So yeah, it's going really fast. I imagine that we were talking about the Doppler shift on the RF communications link, radio frequency communications link, is probably going to be crazy. They're going to have to. You know, I know that during L-Cross, they could tell. We rotated the Centaur around at one point in time because it had water in it. We turned the cold side around to bake it out against the sun, and they could tell that it moved by a quarter of a millimeter per second or something.
Change the delta
Because
V.
the Doppler?
As the steam was coming out of the insulation on the Centaur upper stage.
It effectively
actually
pushed it sideways.
A big thruster.
But they were able. Why were they able to tell?
Because of the Doppler
Because of
shift.
the Doppler. Yeah. Okay. Yeah.
Right, but down to like a small fraction of a centimeter per second.
Oh, that's incredible.
Yeah, it was really crazy.
All right, so here's what we're going to do. We're going to make sure that Vax has a mic because he doesn't right now, and we're going to get a lot more of fun stuff like that. We're going to actually be specifically talking about SmallSats and the SmallSat conference. But before we get into that, we're just talking about launches. Let's take a quick break, go into a launch calendar. When we come back, more of this.
But before we do that,
Oh, no, Lisa, you were. So this is the awkward moment of the show. We're gonna let it go. Lisa was supposed to do the escape velocity patron.
yeah, I messed up.
So-
It's fine because
so
I was
I'm
going to
not-
steal
I'm
that
not
segment
taking the
back
blame.
from you. It's fine.
I'm not taking the blame.
We're bleeding forward the interview and the patron slates. So we wouldn't be able to do this show. We wouldn't be able to do this show seriously without the support and contributions of our citizens. So our Escape Velocity citizens give us $10 per month. They contribute that on Patreon. And we also have our Orbital citizens as well. And the Orbital citizens contribute to us $5 per month. But if you would like to contribute to the shows of tomorrow as well, head on over to patreon.com/TMRO.
Thank you so much.
And now we're going to take a quick break, and when we come back, Ben's going to continue that interview.
Look into her face, determination in her eyes. She won't give up or quit or fall for little fashion lies. Filled with awesome expectation, this girl's a fascination. And nothing in her way will keep her from her destination. 'Cause she's fire walking, she's fire walking. When it's hot, she keeps on moving, the heat keeps on improving. Yeah, she's fire walking, she's fire walking to be free.
My God. Prismara in the chat room says, quote, that was mildly awkward. And I would argue and say that wasn't mildly awkward. That was full straight on awkward. Hey, we're an internet show. It's going to happen. All right. So we are joined by Vax Headroom, Emory Stagmer. You've been on many times. I think one of our most viewed shows under the Tomorrow brand is your Sea Dragon episode.
Yeah.
Which is just an incredible. If you haven't had a chance to see the Sea Dragon episode, that's going back a couple years now.
Yep.
Before we even had the studio space, I would highly recommend it. It's an incredible episode. Someone in the chat room helped me out with like what number it is, and we'll add it in the show notes. We're also joined by Craig Elder, and you were both at this SmallSat conference.
No,
you were at the SmallSat conference.
Emory was working.
Oh, boring.
No, I was camping actually.
Oh, less boring? Well, working and camping.
Way less boring. Not working.
So let's talk. We've been talking about like during the news, we were kind of talking about like SmallSats and whatnot, and like how they launch and a bunch of different things. So, but let's start off with like, we get excited about large satellites, James Webb Space Telescope, these big, huge projects that take billions of dollars. It's really easy to get excited about these things because they're big, huge projects, and you're like, wow, go. But SmallSats, they don't seem to get that same kind of attention, and like, it's kind of hard to understand why SmallSats matter. So let's start there. Like, why? Who cares about SmallSats? Why do they matter?
Absolutely. I'll just say that you can get some big science out of SmallSats these days. What used to take volume of a dorm refrigerator just through the evolution of the products is down into the size of a loaf of bread. A 3U CubeSat is capable of doing just tremendous science. We had possibility of studying the moon's magnetic anomalies using CubeSats as in situ probes. But as you look at the Earth observation capability of a 3U Planet Lab CubeSat.
We still call them Planet Lab here. We refuse to switch over to Planet, but Yep.
So anyway, just the science that you can pack into one of those is just tremendous now. And even though James Webb at Northrop Grumman is going to, I'll just say, open up some just things we've never seen before. As we talk about the Hubble being able to see the first galaxies, James Webb is looking to see the first stars. And that's just stunning to think about what that can do. And yet, if you get enough of these small satellites in an array configuration, you can get some tremendous science out of them. And so the scientific community, other Earth observation, other communities are realizing the benefit of being able to have distributed networks.
And there's a cost benefit as well, right? I mean, James Webb is a little bit more expensive than, say, a SmallSat.
I would
James
say
Webb's a little bit more expensive than almost anything.
It's bleeding edge science, right? I mean, that's going
it
to
really
happen.
is. It's way out there.
Right, but if we pull it back, we talk about like CubeSats. I mean, these CubeSats are now able to take the job and the role of some of these, multi-million-dollar satellites, and they're really driving those prices down.
I would say that a lot of it has to do with the labor required. And labor is the most expensive asset in any aerospace venture. You do something that's never ever been done before, like James Webb, and it's a lot of smart people have to figure out a lot of science and engineering to make it happen. Once you've got this CubeSat form factor, I gave away my 1U Rubik's Cube that the TIVAC people handed out at SmallSat. I do have a whole bag of swag that will go through some of the better stuff this year. But when you think about a 10 centimeter, 4-inch cube, being able to have some standard batteries, standard comm, once the piece gets built or designed, building extra copies is nothing. The folks working at Emory's shop out in Atlanta, Maryland, we can pump out these 4-inch by 4-inch boards. Hundreds a month.
I don't even know. Hundreds at a time. I mean,
So
a lot of them.
we're going from a time where these satellites are one-off, custom-built, like not off-the-shelf anything, every component specific to that satellite, to CubeSats where you can just start stamping out components, and it's kind of like almost like a Raspberry Pi where you have this baseboard system, and then you can do whatever you want on top of that system.
That's a really good analogy, being able to have a standardized, what they call a bus. The spacecraft bus is the boring part. The spacecraft bus is the thing that communicates to the ground and manages the power and manages the health and safety of the satellite. And the thing that people usually care about is the instrument. It's the science that goes on. It's the thing that you're actually, we build the spacecraft bus. So we're building the boring part. And my job as a spacecraft bus builder is to make sure that I'm never in the way. My stuff should be invisible, right? The guys who are doing the science, they're the ones that should have all the problems. I shouldn't have any problems at all. That's kind of my goal. And when you can jam things down to a form factor that's, our avionics stack is 4 inches square by 2.5 inches high.
And we'll stop using former British colony units.
Someday.
10 centimeter.
Someday.
Well, I'm
10
ready
by,
right now.
10
no
by 10 by 6.
FPCUs.
So 10 by 10 by 6. I mean, it's this big.
Sure.
And for instance, we now have the processor that runs in that stack is as good as any processor that's ever flown in space. It's, it's way up there. It has 256 mega RAM, which doesn't sound like very much, but before that I was only able to run like 36, not 256 mega RAM. And so there's a lot more memory on them. It's more capability. It's a dual core processor, and it's built that big.
So there's a very common thread happening in the chat room right now. We talk a lot about like planet labs, the Earth observation, maybe even going kind of to the moon. But the most common question, I'm going to build a bunch of these together. First one comes off of Twitch, which is, what do you think is on the horizon for CubeSats observing other planets? Could they be used to scout future planetary missions? Heliopausing, could we send a swarm of SmallSats towards Mars or on the other planets too? And then Miko 1, what further plans are there to use CubeSats for interplanetary missions aside from Marco A and B, which I believe are those JPL CubeSats going to Mars?
Go to Mars,
now.
exactly.
Yeah, exactly.
I was going to say, there's 2 satellites going to Mars right now. And there, I think that there are 3U, they might be 6U. So a U in CubeSats is 10 by 10 by 10 centimeters. So it's this big.
About that big.
The NASA
like
guys, the
this by this by
Alana program, their mission patch is always a CubeSat.
And it's
clever.
CubeSat size.
That's really
That's how
clever.
big it is. That's how big the satellite.
Yeah. So this is the JPL one. That was from that was Cornell University. This one is NASA Goddard. So their mission patches are always a
Sure.
The size, and that's the size of the
spacecraft.
They're deeper though, right? I mean, they're about yay deep.
Well, a one unit CubeSat.
Here's a 1U.
So a 1 unit
sure.
CubeSat. There you go. 1 unit CubeSat is that big.
And then
right.
2,
and
3.
then you had 2, 3. 3 generally was stacked vertically, and then generally they jump to 6, so they have 2 of those, and you get maybe a little extra space in between.
We had a really nice 6U. The NanoRacks dispenser is 1U by 6 deep.
Is it really?
And they put two 3U spacecraft in series. So when I think of like open the torpedo bay door and out come 2 spacecraft.
Yeah.
And that actually brought us to one of the deployer questions.
Oh,
Can
yeah,
I
we were
jump into that now?
Oh yeah, absolutely. We were talking during the news. We were kind of just talking on the side about like, well, have there any been incidents with deploying? Because when you think about these CubeSats, they're all in this fairing, and there are like a lot of CubeSats generally, and yet they have these deployer mechanisms, and no one ever talks about the deployer. And I was like, well, are there ever any issues with that?
Yeah, and one of the funniest issues, it was a social networking thing between University of Michigan, and any Michigan alums or Montana State alums can correct me on this, but Dr. Brian Gilchrist at Michigan had a team of students build a 3U CubeSat, and Dave Klumpar up at Montana State built a 3U CubeSat, and they launched simultaneously. Unfortunately, one of the instruments in, I believe it was the Michigan CubeSat, had a permanent magnet, and when they came out, sure enough, chink, they bolted together, covering the Montana State antenna. And therefore, for the Montana State to get signals into the Montana State spacecraft, because their antenna was covered, you could relay a command up to the Michigan CubeSat, and when it repeated that command, it would be able to be picked up by this covered antenna. So to talk to the Montana State CubeSat, you had to talk to the Michigan CubeSat first. So like a space telephone game going on.
Yeah.
And somebody there can correct me, but this was straight over lunch between Dave Klump up at Montana State and Brian Gilchrist at Michigan.
But it's kind of like one of those things that you don't know that that's going to happen until it happens.
Sure.
Right?
You would never think of it. They're launched like this.
Yeah, they're just going behind the other. And the other thing is that they've found that originally some of the launchers had they generally have a rail on them, and the satellites will slide out on these rails. There's a spring-loaded launcher behind them, so the spring will go out. And if the rails are not perfectly aligned, or you have more than 2 of them, the vibration or whatever, they can actually torque and jam, and so then spring can't push it. So you have a deployer failure. So there's a couple different systems out there that have Some have failed, some have been reworked. And
Have there been deployer failures in space
yeah.
for CubeSats?
Yeah.
I'd love to hear from NanoRacks, Tyvak, Planetary Systems Corporation, PSC, Walt Homan in Maryland. To my knowledge, I have not seen any failures of those.
It's been a while.
Of those systems. Those are very mature.
Yeah.
And,
I think early on there was more failures, and they've gotten better, right? And one of the things that we talked about, you talked about the size and the cost and things like that. When I came on, I think it was about a year and a half ago, and talked about Northrop Grumman's CubeSat, SmallSat avionics that we're building. One of the things that I related was like, how much cheaper does it get? Well, it's like the reverse of the rocket equation. We talk about this thing called the tyranny of the rocket equation, where the bigger it gets, the bigger it has to get, because you have to have more fuel, and then you have more mass,
you
and
have
then
to launch that fuel.
Fuel and fuel and fuel. You have to launch fuel to launch more fuel. Well, when they get smaller, the reverse happens, right? So the smaller it gets, the smaller it can get. So, right, you need, if you cut the mass by a factor of 10, well, then you're cutting your reaction wheel sizes down by a factor of 10, and then you need 1/10 of the batteries and 1/10 of the power, and all of a sudden that's even smaller now than it was before, and so the systems get progressively small, almost exponentially smaller as they get smaller.
But still as powerful, right? So they're smaller, but they can still do as much as their larger.
You're still limited in power. You're still got to get rid of heat. You've still got to do those kinds of things. But again, technology has moved forward. So some of the things that we used to have to worry about, for instance, the way that solar rays come into a power system, generally you would put a blocking diode so that the power, if the solar ray should short circuit and want to pull power back off the satellite, the power can only flow one way. Power can only flow into the satellite, can't flow back out of the satellite from another solar panel back out to this one. So you'd block it, right? The problem is that those are very power hungry and they generate a lot of heat if you're going to put a high power diode in line with those things. Tens of watts. Well, CubeSats are only generally tens of watts anyway, right? And so all of a sudden you're pulling a lot of your power down with heat. Well, some of the more mature technologies, things like what they call a peak power tracker, that allow the satellite to more efficiently use the power coming off the solar ray, they don't have blocking diodes. And because some of the electronic switches and solid state switches and things like that have gotten more efficient, our solar ray interface is now like 98.6 or 98% efficient. So there's almost no heat, right? So now we can start talking about CubeSats that aren't 50 watts. Now we can start talking about CubeSats that are 500 watts. So a 500-watt satellite's a very, very different satellite than a 50-watt satellite.
Ben, your audience was asking about deep space or CubeSats around other places. One thing that's really fun, one of my favorite stops at SmallSat was the NASA booth, where they were talking about the big SLS rockets, but CubeSats are almost just in the noise to a big rocket like this. And
although imagine how many CubeSats you could launch on the Space Launch System.
Well,
actually maybe I'm about to figure out.
They're about to figure out that the SLS has a real good information available through NASA Marshall Space Flight Center down in Huntsville that talks about the secondary payloads that are on board the upcoming SLS demonstration mission. And as you look at what some of these SmallSats are capable of, as Emory was saying, you get enough power and have enough, I'll just say, size, weight, power capability, you can really get great science. Now I'm going to put kind of a limit into this. Much like this Parker Solar Probe, if it gets too close to the sun, you can generate a lot of power off a 10-centimeter solar array, but you have just horrible thermal problems getting rid of that heat that you brought in. And yet, if you get out to Mars, the solar intensity at that distance is so little insolation. The intensity of the sun at that point is so small that you end up flying large solar arrays, much larger than the satellite itself. I mean, way much larger. You get out to the asteroid belt, you're almost can't do it with solar power.
Right.
So if you were to do SmallSats around, I'll just say around the moons of Jupiter or the rings of Saturn, those would basically need to have their own power source with them. So I can't. The views I espouse here are purely my own.
Well,
and,
you were at the
look
conference.
yeah.
Did anyone have something to solve the power, the interplanetary power problem?
So it really comes down to: are we as a society going to take the risk of being able to allow launching RTGs, radioisotopes? They are dangerous. They are lethal. But
how dangerous is an RTG though? That's in the size of a CubeSat, because the CubeSat doesn't need that much energy.
Right.
So we're not talking about something like
it's
an RTG for like
it's
curiosity.
a couple of grams. It's a couple of grams of plutonium, but how much of that do we have? U-238. How much of that do we really have around to put into SmallSats? And there's not as much available as you would think here. Now, one of the things that was just stunning me this week is the Chinese Chang'e 4 lander is going to operate on the far side of the moon. The first human far side soft landing is coming up in November or December. And being able, they're going into the Aitken Basin, which is where Emory and I are very thrilled after the L-Cross mission, which was on the southern rim of the Aitken Basin, and the resources that we found there. If we can find some of those, I'll just say radioactive materials, the stuff of stars, if it's more bountiful in like the Aitken Basin rim where the crust of the moon was stripped away and you got down into the heavier elements, if you could access that, those radioactive sources, that would be a tremendous way to fuel future spacecraft instead of taking that really precious water off the moon and turning it into fuel. I could see going after radioactive sources and mining those from the moon and using that as a safe way. If I had my choice, I would have no nuclear power on Earth. I would have it all on the far side of the moon and beam the power back here to Earth. Because if you had a containment breach or something, it's space.
The moon's basically a wasteland anyhow.
Except at the poles.
Except at the poles, yeah.
But the poles are paradise.
Yeah.
The poles are paradise.
They really are.
Actually, that'd be an interesting place to have a lunar colony, and like just the observation of Earth from the lunar poles would be pretty cool.
Yeah, I could see a robot colony.
Yeah.
Humans are messy.
Yeah, humans don't like space. So yeah, but you still, come on. Well, that's an after dark conversation. So back on that same topic, going back a little bit, Neuropilot off of Twitch asks, can any non-government organization get plutonium for a CubeSat, right? I mean, there's radioactive isotopes.
Not to my knowledge.
Going to be governments only,
I mean, dental stuff for X-rays are not what you'd use for a power source.
Yeah.
So what else did you were at the CubeSat conference. What were some of the things that like really piqued your interest? Like you're like, oh, this is awesome.
This is really awesome, and it sounds silly, but it was the networking opportunities were awesome. I have to give a shout out to Utah State. So every August, Utah State for years now has been hosting the SmallSat conference every August, and it started out really small, just some enthusiasts, and then it became the universities getting together because CubeSats are such a wonderful learning opportunity. It's not a lot of money if you mess up, and you can do a lot of simulations and do a lot of great science without a lot of investment. But as the commercial aspects started coming up, the CubeSat conference, SmallSat conference, just blossomed from 100 people to 1,000. I think we had over 2,000. 2,500 there this year. It was stunning.
That's a lot of people in Logan, Utah.
And
they packed the city out for a week. It's crazy.
And the networking opportunities, I'm wearing the lei from the Northrop Grumman Orbital, or AIG, the STK folks, graciously sponsored a luau at the Ryder Mansion with fire dancers and a specialty cocktail called Situational Unawareness. It was absolutely lovely Mai Tai. And I know that the Rocket Labs folks had a great band one night, and of course everybody in between sponsored parties will go to the White Owl pool billiards tavern and shoot pool downstairs or go up to the upper deck. I remember a year or 2 years ago, had all the right people sitting around looking up at the stars. In Logan, Utah, you can actually see like all the stars. And sure enough, the space station's coming over at about 9 o'clock at night, just brilliant, brilliant white. And we're all sitting there. It should be going into eclipse about now. It should be going into eclipse. And you get this many geeks on a rooftop deck, couple of beers in us, thanks to the Braxton folks, had handed out tokens good for beer, and it's like, wow, these are actually people who know that it's going to go into eclipse, and that beautiful bright light is going to go out right now. And it was like, oh, how cool is that? And there's people up there.
Yeah. Humans up there.
So the networking opportunities, just being around all those people is just the really, really cool stuff.
I was doing almost exactly the opposite. I'm at a camping trip in northwestern Pennsylvania. That's a medieval reenactment. Okay, this is a big event.
I am not surprised at all.
Yeah,
I've been doing that. I've been doing that for 27 years, I think.
Yeah.
Wow.
There were 10,500 people camping there.
Oh wow.
So it's a big event, right? And I'm out standing up at the top of one of the hills where there's a road, right? And people are walking up and down the road, and they're partying or drinking or just going from camp to camp or whatever they're doing. And I'm actually pointing the space station out to people. And they're like, "Oh, that's so cool! There's people up there." Wow.
Did you do it in character?
No. My lords and ladies.
That would be amazing.
The harbinger of the heavens. No.
So, networking.
One other thing.
Yeah.
I have to say that engineers are really peculiar people. So the folks at Virgin Orbit here in Long Beach had a mocktail, that for the afternoon during all the presentations or during the exhibits, going booth to booth, there was kind of everyone, cocktails are being served at the Virgin Orbit booth, and they gave away lovely cups. And the mocktails, there was a rocket fuel mule. It was a mock Russian mule. I had the Cosmic Girl Mai Tai is what I chose, and they had a couple other fake drinks. But the other funny thing about engineers, we would have an ice cream break every afternoon.
Ice cream break.
Oh my God, Lisa over there is just freaking out. She started bouncing.
Did you try the blue color?
Right, absolutely. It was the Aggie Mint.
The cool blue mint. Yeah.
Cool Blue Mint. And I brought the folks at
I've lost control of
Maxar.
the show. Yeah.
Oh, absolutely. So Space Loral, SSL up in Palo Alto and other places is now rebranded as Maxar. They had the color-changing ice cream spoons.
That's cool.
You put it in the ice cream and it goes blue, pink.
Oh, it's a thermal.
It's a thermal ice cream thing.
That's
And
actually kind of fun.
So this was fun.
So wait. So Space Systems Loral, and then they were like, no, now we're just SSL, now they're no longer just SSL.
Well, they were
now
McDonnell Douglas Associate MDA when they were tied up with the folks up in Montreal, and a really powerful synergy between Canada and the United States in that company. It made it a little difficult for ITAR and EAR reasons, but they were because of that those restrictions. Part of their business, the government business, I believe, has come back off as a wholly American-owned, and they all went under the Maxar brand. So I'll just give a shout out to Mark Hansen and Nagar up in the Bay Area. If you ever get up that way, they've got some neat stuff going on there, including SmallSats. Yeah.
They also have.
I could talk forever on this.
Yeah, they have Stealth Space Group up in the Bay Area as well, which is
neither confirm nor deny.
Yeah. So they'll be launching SmallSats, as I understand it. Also, all right, cool. Yeah. Just a couple more questions from the chat room, then we'll head to break. I lost my place. I'm sorry. So here we go from Smoky Dirk. Do you think it's possible to build a CubeSat lander for bodies like the moon or smaller? So you talked about China landing on the dark side of the Earth. So
that's
not
a big
the dark
lander.
side, the far side of the moon.
Yeah.
There's not I know.
The dark side is in those permanently shadowed craters at the poles.
Sure, there you go.
Dark means knowledge, not light and dark. We had a lack of knowledge about the far side of the moon, and that's why it was called the dark side.
Oh, thank you for correcting that.
That's an older kind of a use of the word dark.
Anyway, he was
That's why
saying,
it's
could
the
we
dark
soft land?
ages, for instance, because there was lacks of knowledge. not because
Interesting.
The sun doesn't shine.
Well, then it is the dark side of the
can
moon
I give
because
this-
there is less knowledge on the dark
Can
side.
I give the snarky answer?
Oh, yeah, absolutely.
So as the L-Cross spacecraft program manager and Emory as the software, absolutely you can land a CubeSat on the moon. It's just depending, how many pieces do you want? So
Fewer
that
pieces,
in mind,
harder.
That in mind, if you can,
One working piece,
Right.
very hard.
no, but the one
What do they call
working
it?
piece,
Litho breaking. Yes, right.
So much like the egg drops that everybody gets to do in high school or in vacation Bible or whatever, you end up, if you have your science instrument such that it's in the I'll just say a pretty rugged 1U cube, and you were to put, I'll just say, an airbag around it.
Sure.
Absolutely. You can't aerobrake at the moon because the atmosphere is about 18 centimeters off the surface and varies wildly over the course of the 28 days. But you could absolutely just
Slam
airbag deploy CubeSats onto the moon, and that would be a pretty straightforward thing. If you had a
That sounds like a fun piece of engineering.
Yeah. So a 20.
All right, community of tomorrow, I want you to airbag,
I'll suggest-
build an airbag for a CubeSat for a lunar
And
landing.
I'll suggest 27U, so it's 3 by 3 by 3, with a 1U science payload in the middle, and everything else is like crumple zones.
That would be
Slash
kind of awesome.
Deploy and crumple.
Progressive crumple zone. So you get,
Yeah.
Yeah, because you're gonna have a bit of velocity when you're
And
going
the other thing
in.
about CubeSats, they don't have much attitude control. I would recommend don't waste your time trying to do attitude control on a lunar lander CubeSat. Just let it have it symmetric enough that it can hit any orientation.
kind of like Pathfinder.
Oh, yeah.
Like the Mars Pathfinder.
Yeah,
It
just
was-
the airbag.
Yeah. Well, it was a tetrahedron when it landed, and then it unfolded, and whatever side it landed on, when it unfolded, the lander ended up on the bottom.
Yeah.
It was
Amazing
really, it was
engineering.
very
Yeah.
clever. Very JPL.
JPL,
again. JPL
yeah, all
again.
the really cool stuff.
Yeah,
JPL.
super
Oh,
clever.
come now.
Yeah.
All the cool stuff you can talk about.
All right. That's fair. From Hanny's Vorswarp from Twitch asks, can CubeSats be multifunctional, or is it usually one task per CubeSat?
Multifunctional.
Oh, absolutely. Yeah.
It just depends how small is your sensor. There are some amazing, I'll just say, laser comm experiments and stuff that are just like little LEDs, and just do great work. All sorts of the science discussions from the SmallSat conference. If you get a chance, find somebody who has the presentations on science, SmallSat science, and you'll just see, oh wow, I can do this and this and this in a 1U, and I can add this and this and this for a 2U. And by the time you get up to 27U or a half SPASat, it's like, oh my God, I can have an entire.
Well, that's a really good point, is that they will make all the presentations available from basically all the presentations and all the non-classified presentations. They will all be made available publicly.
Oh, that's cool.
I haven't seen them yet,
They're
but
not-
they generally are out there, and if you want to go look at the ones from prior years, they're always amazing. They're always just like, you can do that on oh my gosh.
And Ben,
the little tiny robotics that people are doing, and actuator movement, and just really super precise little machining, and just really brilliant stuff.
Quick shout out on a lunar lander. The Chinese on the Chang'e 4 are having a little biosphere with silkworms, and it wasn't spinach. It was types of I'll just say oxygen producing things. They were going to make a little tiny terrarium that goes with it.
So that's going to be the first life that we've had on the moon since the 70s.
That's right.
That's going to be incredible.
That's
going to
cool.
be really. That's going to be an and the first life ever on the far side of the moon.
That's
That's
right.
going to be really incredible.
Right.
Yeah, and like I say, I wish them the best, and hope that some of the folks listening here can come up with putting something live on your lunar lander. May I also say that with so much like my status on nuclear power, just put it on the far side of the moon, I would absolutely be an advocate for any bioprocessing of new biological agents. Do them on the far side of the moon where if there's a problem or a breach, they are exposed to space and do not take out our world. So I would absolutely coming up with bio experiments, bio labs, robot-tended labs on the far side of the moon is huge. And I would go one step further to, boy, if we could get all the lawyers to the far side of the moon.
See, you do want to put humans on the moon.
I do.
See, you do.
Well, that's a stretch there.
All right. Last question, then we're going to head into break. This is from Chiwicked. He asks, and this kind of goes to the sizing of CubeSats. Says, do you think CubeSats will remain the size standard for university sats, or will the miniaturization of technology mean that Pocket Cube, 5 centimeters or 2 inches, start to overtake that field?
You want to handle that? Or?
No, they've already got, well, Pocket Cube is one standard, and there's another one called Pico Cube. It's another one. JP Aerospace, who has been on the show more than once, has PongSats, which are ping pong ball size. There's already a number of standards that are shrinking things down even smaller. Those sizes tend to still be quite experimental. You're not going to have a super robust set of technology that's going to be able to survive in space for any amount of time, as opposed to the CubeSat level stuff, which we've just gotten to the point now where those things can be robust. The avionics that we are building and that some other folks are building are pretty robust and can survive in space for years at low Earth orbit. Our stuff can actually survive in space. Deep space around other planets outside the Earth's magnetosphere in particular for years. So,
would you say the future is CubeSats? Like, are we moving away from these giant satellites and kind of coalescing into CubeSats, or is it's kind of like the Richard Feynman quote. There's plenty of room at the bottom. It's not that we're not going to build large things, but we can build more small things and make them robust and have them to the point where they can be a full-on science mission, as opposed to just an engineering demonstration or a educational learning experience for universities or things like that, which is what they had been up until about 2 years ago. And when I was at the CubeSat conference 2 years ago, we saw that people were starting to say, we want to be able to have full-on, robust civil space science missions that are gonna last. We're gonna spend the extra money to build a robust instrument, right? And we want that to be able to orbit the Earth for 3 years, right? And the spacecraft bus didn't exist at the time, and that's what we saw as an opportunity. That's why we went and did what we did. So. Yeah. Awesome. All right, guys, that was a lot of fun. I think we're going to bring you back for After Dark, talk a little bit more about just random stuff, maybe CubeSats, maybe not CubeSats, but definitely some space stuff. But before we go into break, I did want to say thank you to all of our citizens of tomorrow. These are people who have contributed $10 or more to this specific episode. There are Escape Velocity citizens. And unlike at the beginning of the show, where Lisa, for whatever reason, decided to go to the orbital slate, and Buddha, kudos on you for being able to pull that up at the last minute. We also have our orbital citizens. This, Lisa, I'm looking right at her. You can't see me doing that. Lisa, this is where they go in the show, just so you know. These are people who contributed $5 or more to this. She's blushing to this specific episode. To find out how you can help crowdfund the shows of tomorrow and all of the different reward levels, head on over to patreon.com/TMRO. All right, we're going to take a quick break, and when we come back, comments from our citizens. So stay tuned. We'll be right back.
Science. It both draws us together and tears us apart. Brings discoveries to cure us and threaten us. It is neither good nor evil. It is what we decide to make of it. There is so much more to learn. And we are curious. Together, let's explore the science of tomorrow.
And welcome back to Tomorrow. Now, before we get into our questions and comments from last week's show and ideas from the community, we just wanted to give you a quick wrap-up of what we talked about last week. So last week we had Chuck Ryan talking about the Space Shuttle resolution, which was like a shuttle mock-up and trainer that he built himself, which is pretty inspiring, actually. I don't think I could build something like that myself. So really, really good interview.
Yeah, and also I will add one thing we're changing this week a little bit for our show is that while we will be talking about comments from last week's show, we're actually opening it up to just general comments from the community. So we're no longer referring to it on Space or Science as comments from last week's show or last show. It's just comments. So if you have something awesome, whether it was related to the last show or not, we're going to bring it into the show from now on. But we're really only going to focus on YouTube, Discord,
and the community forums.
and the community forums. Is that correct?
Yeah,
that was
that's
correct.
the main
Yeah,
three.
those are the main three. Yep, exactly. So there you go. All right, let's get started.
Cool. So our first comment comes off of YouTube, and it's from Eric IRL, who asks, Chuck is an interesting and inspirational guy. Is resolution finished, or can it be salvaged? To which I would like to bring up the next comment, which leads directly into this, because someone from our community, Loopy, actually posted on our Discord channel. It was awesome to see this happen like in real time.
And yelling.
I need to impersonate this. So Loopy says, "Is that the thing on Courtney Parkway just past Air Liquid? I saw that the other day."
On the arm movement.
But seriously, so Loopy actually has some photos that they took. So this is the current state of the resolution, which
I mean, maybe salvageable, but I don't think that nature wants you to have that back.
Just you set it to some duct tape and give it a bit of a clean, like a pressure hose. Put some skins on it. It'll be fine.
Some paint.
It'll be fine, right? We can do that. If only we knew someone that could like build things like
Out of wood.
Yeah.
Like space things out of wood. If only there was someone on the community of tomorrow that could build space things out of wood as we all turn and look at Dota. All right.
So yeah, to answer that question.
As much as I love the space shuttle, I cannot rebuild that.
Yeah, I think nature may have already had its way a little bit too much with that one.
Oh, nature. Man. That's kind of sad. But I don't think it got looked after, right? Like I think it just
kind of sat there. And
it looks like it needs a giant umbrella.
Oh, to protect.
Did you add more glitter to your hair in between? I just looked over there, and there's like all of this glitter in your hair.
It's self-replicating. Hello, remember? Throwback. Which orbit was that?
Seriously, I look over, and it's just like glitter all up on, and it's like shining in the light. All right.
Oh
Next
goodness.
up.
I'm trying not to move too much so it doesn't like fly everywhere.
Yeah,
it's already on the chairs.
They're nano
diamonds.
They're nano diamonds. Yes, looping it back to news. They're nano diamonds.
Exactly.
Smoky Dirk has a great comment in the chat room here. The glitter has become self-aware.
Oh no! AI glitter.
All right.
That'd be crazy. Yeah.
Our next comment comes off of YouTube from Kevin F.
Kevin F. pandered to Lisa, and it worked.
I am so disappointed. Not one mention of unicorns the entire episode. Of course, I mention unicorns to get your attention and perhaps get mentioned as a comment. My real question is about curiosity. Has anyone heard from it? Is it lost in the dust? Unicorns.
I will admit it worked.
Jared would be a great one to answer this question, but apparently there was some sort of like Doppler shift, pretty much a false signal. There were some people that thought that we did get not from curiosity. Curiosity is fine. I think what Kevin F here is actually opportunity.
Yep.
Because curiosity is fine. We're still in contact with curiosity, but we have not yet heard back from opportunity.
And there was we got a signal back, and it looked like it was in Opportunity's frequency range, but it turned out to be a Doppler shift. Bringing Doppler shift back into the show again.
You guys talked about it earlier.
Yeah, exactly. So it actually had shifted over, and they went, So still dark, but I think that's actually still okay. It doesn't mean anything bad. It just means, no, we haven't heard back yet.
And speaking of Jared,
because we had giving our secrets away. We had a false start in the third segment. We did. So Jared is out. He's at the doctor today, doing a little thing. So we just wanted to say we miss you, Jared, and we're excited to have you back. And I hope you feel better. There you go. That's as human as I get.
Oh my God.
Get well soon, buddy.
Yes.
All right. On that note. Our next comment comes off of YouTube as well, and it's from Ryan Block B5. And Ryan Block B5 says, I think it would be a great idea to use Kerbal to make animated diagrams of the rockets that were launched that week. It would be incredibly informative to see a blowout of the different segments and boosters. That would also be a way to get some operational vital numbers on screen. You could do a virtual size comparison of the rockets. This would be super helpful with Chinese surprise launches, and most of us might never see a launch in person.
Yeah, actually, I think that's an interesting idea.
I like that a lot.
Yeah, I do too, but I think for that to work, we would need the help of the community to kind of build some of these things.
Yeah.
Because, I mean, we all have day jobs as well, and we're already putting the show together, and it does take a good chunk of time. So if that's something that interests you, head on over to community.tmro.tv, and we can, let's see if we can figure out how the community can help build some of these elements together week after week and make sure that they're ready to go for the show, because we can't do them like 10 minutes before a show, right? This all has to be kind of pre-produced and ready to go. So,
If there's like any animators out there that can do that, that's really cool.
Well,
like
I mean,
anyone who works with Universe Sandbox, you know, do like a rocket version of that. But I guess it would come from like RPG, right?
Yeah, some Kerbal gamers
Yeah.
that can.
My brother can do. I'll call my brother up. Hey.
I know quite a few modders in the Kerbal community, so we can actually have rockets that look like the real thing and not the cartoony rocket parts that Kerbal Space Program already has. And I mean, I have programs that I can record gameplay so we can have video, not just screenshots and stuff like that. One great mod is Chronal Vessel Viewer, which gives us that exploded view of stuff so we can have really nice looking diagrams and everything like that, especially if it's the real looking parts and satellites that actually look like the real thing. So there could be a lot of potential here, but just like Ben was saying, it takes a lot of time. To be able to put those together, even for just a quick little clip, does take time. So yeah, get on the community forum. Let's talk about how we can help each other and what exactly we would want to see for this. And let's make that happen.
Yeah, I think it'd be pretty cool. But I definitely think this needs to be a community effort. But I am excited about the idea. I think it's pretty cool. We did talk about it in Discord with Mike a little bit, and he did show some of those views. And I think there's a way to loop that into Launch Minute in a way that makes a lot of sense. The Launch Minute graphics, I think, are temporary right now. That banner at the top, I think it's a little hard to read. It's not quite what I want. I do like the countdowns. I know some people don't, but I think it adds a certain energy to it. Like there's this, because launches have that energy when you're watching them, and Launch Minute recreates that energy, that like slightly nervous energy. And so I like that there is this slightly nervous energy during Launch Minute. So anyhow, there you go.
A lot of people in the chat room are suggesting Scott Manley. Raj Luthra from YouTube asked, how about getting Scott Manley on the show?
Well, we've had Scott Manley on the show,
Yeah, we have. Back in, I believe, Orbit 10, the very first episode of Orbit 10, 10.01. We'll probably put a card on YouTube so you can click that and go
watch
watch
10.01? I think it was like 10.02.
It might be 9.01.
Yeah,
it's either 9 or 10.
I think 10.01 was
gameplay as well. So
say that again, Mike.
I'm sure he'd be down. Everyday Astronaut does lots of Kerbal gameplays as well. So
Tim Dodd, the Everyday Astronaut. Yeah, absolutely. Yeah, so Scott Manley, Tim Dodd, the Everyday Astronaut, which, by the way, is the only way. If you ever meet Tim Dodd, the Everyday Astronaut, in person, I do request you only ever reference him as Tim Dodd, the Everyday Astronaut, and never shorten that just to Everyday Astronaut or Tim Dodd. It is always, always, always Tim Dodd, the Everyday Astronaut. I don't actually have a real good reason for that. I just enjoy it. So, and I do that to him all the time. You'll notice I do that on the show. And I actually do that legitimately in real life.
So stupid.
He'll stay at our house for a couple days. You know, he's going out doing things, and I always refer to him as Tim Dodd, the Everyday Astronaut. And I want to get everyone to start to do that, just to make it ever so slightly awkward. That is my request of you, the community. All right.
I would end up stumbling on my words every single time. So, okay, I'm ready for that, but
No, you can get it. Tim Dodd, the Everyday
Hi,
Astronaut.
Tim Dodd, the Everyday Astronaut. Oh, okay, there we go.
It's not that
But
hard.
I feel like it's something you have to say fast. Like, hi, Tim Dodd, the Everyday Astronaut.
Yeah, it's not bad.
Like
It's not bad.
Yeah.
So thank you to Smokey.
How do you feel about this?
Thank you to Smokey Durg in the chat room, who did bring up that Scott Manley was on 8.01, so it was actually a couple seasons away from 10.01, which I believe
Time just flies.
Yeah, 10.01 was Universe Today, if I remember right.
Oh.
And I remember that because it was all the new graphics. And to this day, he's in the graphic template for everything because he was the first. Yeah, anyhow. All right. Fun little behind the scenes moments.
Wow. Okay. Before we end the show, we're going to do a big thank you to our citizens, and this time I'm actually going to do it properly. So we couldn't do the show without your support. So thank you so much to our Escape Velocity citizens. These people give $10 or more per episode, but we also have our Orbital citizens. Thank you to our Orbital citizens as well. They contribute $5 per episode. But we also have our suborbital citizens who contribute $2.50 per episode. Thank you to you guys as well. I hope you have enough time to find your name on the screen, because there is lots and lots of names, and there's more every single time.
It actually says in the rundown to hold an extra moment on the suborbital slate so people can find their names. And I think by me saying that, we've delayed long enough.
I think totally.
Yeah, okay, cool.
Because we also have our ground support citizens as well, and these people will contribute between $1 and $2.49 per episode. So thank you to these people as well. There are even more names, and this list gets bigger and bigger and bigger every week. And it just blows my mind that some people think that our content is engaging and entertaining and informative enough and fun enough for them to contribute their hard-earned money. So hopefully that was enough time for you to find your name. And if you would like to help support the shows of tomorrow as well, head on over to patreon.com/TMRO.
Thank you.
Boom! That's
Boom.
how we do
Great.
Patreon
You
slate.
got it. You spent enough time on each slate. I will say before we go, before we say goodbye for the space show, we do have science coming up. So there are people in the chat room who are like, goodbye, great show. Don't leave just yet. We have science coming up today. So that's going to be awesome. And I expect that's a slightly new format. So it's going to, if you enjoyed watching the awkward on this show, and let's not fool ourselves, it was awkward. Don't worry. We'll be bringing it back for science as I spit. I'm sorry. All right.
Saw that.
Yeah.
Awkward.
I'm just spitting out the awkward.
Oh man.
So, all right.
It's going to be in about an hour. We're going to be talking origami underwater robots. So
What?
That's going to be awesome.
Yeah.
I
Whoa.
also wanted to turn everyone's attention to the community forums at community.tmro.tv. I'm considering changing the citizen reward levels and getting rid of ground support and moving everything down one. So suborbital becomes the new ground support. So you wouldn't be paying anymore, but you'd be getting more rewards. And I'm actually curious as to what additional rewards you, as the citizens of tomorrow, would like for helping to support the shows, and what you're comfortable with, because I think it's time for us to kind of review it, go over it, and go, what are you getting out of this? What can we do that's better for you? Because you're helping to make us do these shows week after week. So head on over to the community forum. I've got a little thing over there. I think I wrote it very confusingly as if I was getting rid of ground support and you wouldn't be able to contribute at that level anymore. That's not the case. You'll be able to contribute at the same levels, but you'll get more for your contribution. That's the plan. So we'll have 3 levels instead of 4. I don't know yet. I'm looking for your feedback.
And also, like, if you don't have the ability to contribute financially, some things that really help us is sharing on social media, or even just hitting the subscribe button is really helpful as well.
Yep, absolutely.
Yes.
Okay.
All right. Well, that's our show. Thank you so much for watching. After Dark is up now, and then science. So stay tuned. We'll see you next week.